I still had the motors used to open and close the tray of an optical drive after building my tiny plotter. Those geared motors became part of a CNC machine. Same as version 0.5, CNC 0.6 was created with low-tech tools. All you need is a metal and a wood saw, a soldering iron, a file, a caliper, metal shears or old normal scissors, a screwdriver, a folding rule, or at least a part of it, and some epoxy. Additionally, I used some hot glue and I've made 2 wrenches from a piece of iron. The frame is made of 19mm chipboard. You can get the step-by-step instruction including the schematics on the project page. The horizontal axes are driven through 3mm threaded rods. On the bottom side of the tables for the X and Y axis there are brass nuts soldered on perforated metal stripes. If your soldering iron is powerful enough, there is no need to use a candle. A hole is needed at the center of the tiny 10mm blade. It's an easy job if you have a drill machine, some thread and a long screw is needed if you don't own such an electric helper. The wood is sealed with some wax. You can also use some varnish. Bend the metal construction with a caliper to make the threaded rod run straight along the blade. There is noticeable clearance when using just one nut. Attach the second metal stripe with the brass nut in such a way that those clearance is reduced. The less clearance, the more friction. The right adjustment is always a compromise between low clearance and not too much friction, remember that the drives are not very strong. A piece of foam is wedged in the mount. That sponge operates as oil reservoir, the threaded rods should always be well greased to reduce friction. You can grease the threaded rods through the tiny hole at the assembled machine. At the other end the threads are guided by pieces of fiberboard. Once more the needed hole can be drilled without a machine. 2 screw terminals keep the threaded rod in place. Some drops of oil keep the friction low. The linkage between the motor and the threaded rod is made of a paper clip and some epoxy. A short piece of a 3mm rod is glued on the gear wheel at the output shaft of the drive. The drive is connected to the threaded rod with another screw terminal. The vertical axis is actuated by a standard servo. The electronics, consisting mainly of an Arduino Uno and a double H bridge, is mounted at the backside of the machine. An old computer power supply feeds the machine with electricity. The H bridges are connected to the 12V line. Since 12V is too high for the motors, the voltage is stepped down to 7V by pulse width modulation. That's just enough power to move the horizontal axis of the CNC machine. The tables slide on the edges of the aluminum bars, causing a relative high friction considering the low power drives. The first items processed by the machine are cut from 3mm plastics. It are discs with a diameter of 37mm. The edges are not perfectly cut, thus you have to smoothen the parts with a file. Those discs will operate as wheels in order to reduce friction along the X and Y movement. Instead of the self-made plastic discs, you can use tiny wheels available in all hardware stores. Even the cheap wheels or ball bearings are usually from better quality than the discs I have cut, but I like the idea of using a CNC to improve its own design, its machine evolution. With the tiny wheels, the friction is reduced clearly and the motors are turning faster. so let's plot a test pattern with a ball pen. The software runs on Linux in a terminal window. You can choose a file and set some machine parameters. The plotting is done with maximum speed. The test pattern consists of several concentric circles and 4 lines with an angle of 45 degrees between 2 lines. The plot is compared to the same pattern printed on a foil using an inkjet. Considering the low-tech construction, the result isn't too bad. The maximum speed of the CNC machine is around 3mm per second. The drives are mounted in such a way that they can be replaced quickly. This geared drive is from an old printer and it has a 12V motor. It is clearly faster. We get a maximum speed of more than 4mm per second. Nonetheless, I am using the low power motors from the optical drives because I love minimalist machines. Next, the machine moves to one point from 2 different directions. That will show if the machine is adjusted to low clearance. As you can see, the result is very good. However, you have to consider that there is no side load on the ball pen. You can in fact deflect the tables easily by hand. The threaded rods are weak and so easy to bend. The linear guides are composed of aluminum angles and nails with pieces of fiberboard. The fiberboard is soaked with oil to reduce friction. Even if that mechanism is adjusted to lowest clearance possible, the angles deform under load. The hinges of the vertical axis are made of 2 stripes of perforated metal, by what there is almost no clearance in horizontal directions. However, you can deflect the pen easily in vertical direction, which doesn't matter that much, since the machine is designed to cut 2-dimensional items. The positioning accuracy along the vertical axis is clearly lower than along the horizontal axis. 10 steps in vertical direction equal a movement of more than 2mm. 10 steps in horizontal direction equal just 0.3mm. The router tilts with movement along the vertical axis, causing oval drill holes in theory. As you can see, that doesn't matter in practice. 10mm chipboard is engraved next. In the first run, the router is diving just slightly into the material. The chipboard is never dead flat and the drill might break if it goes too deep into the wood while moving along the path. The router is lowered for a second run, by what the drawing lines become clearly visible. The outline is processed in another 5 runs, until the chipboard is cut along that path. Note that the router bit heats up strongly whenever it dives too deep into the chipboard, as can be seen on the smoked wood along the cutting line. This machine is not made for cutting wood with a thickness of more than 5mm. As demonstrated before, you can process plastics with that CNC. The machine cuts a gear wheel with 60 teeth. The gear wheel has round teeth that are calculated by the software using several parameters. Always cool the material with water to avoid the plastics from melting. Once more, the material is cut in several steps. Parameters such as feed rate or cutting depth depend on the material to cut and are empirical values. My first attempts in cutting plastics were failures. You have to make your own hands-on experience with a CNC machine, and in doing so, you will scrap more than just one part. The gear wheel is not perfect, but it's good enough to demonstrate the working principle of a transmission. This simple gearbox is not for high speeds or high torque. The 1mm aluminum plate is really heavy metal for this machine. The feed rate is set to a very low value. A high side load is needed to cut the metal, and as demonstrated before, that causes distortion of the threaded rods and the linear guides. That clearance can be reduced by professional wheels or ball bearings instead of the plastic discs I am using, and by stronger threads. There is space for improvement and own ideas. The result is eventually acceptable, but definitely not very good. Before cutting, you should have a close look at your CNC. The left aluminum disc with a diameter of 18mm was cut before, and the right disc after readjusting the machine. 3mm Depron is more easy to process. The machine can cut the material with maximum speed. There is a second layer of waste Depron underneath the material to be processed to avoid the router bit from diving into the wood. You can also melt Depron using a soldering iron with a 1mm copper wire at its tip. That's much more quiet. The heat at the tip depends on the length of the copper wire, and it must be enough to melt the Depron, but no more. Too much heat widens the cutting line and increases the bad smell of evaporating plastics. Depron is a proper material to demonstrate the working principles of a CNC. Besides the fact that it is easy to process, it is very cheap. Finally, I'd like to engrave glass. The router isn't mounted perpendicularly to the cutting plane, but with an inclination. The diamond milling cutter should always be cooled. I am using water with some drops of dish liquid. The result is really good, since there is almost no side load during engraving work. That's all about CNC version 0.6 for now. You can get the step-by-step instruction, the parts list and the schematics, as well as more CNC machines on the project page. Thanks for watching, and I'll be back.